Welcome to Breadboarding. This is video 4 in the Breadboard PC series, and in this video we're moving on from doing the reset and supervisor circuit in the previous video to do the system clock. So you can see from a high level plan we've completed the reset and supervisor circuit. Now we're going to move on to the clock. In this stage of the project we're trying to really build an equivalent of the Nanocomp from the 6809 project that actually runs on the Intel 8088. And at the end of this stage, we should have an LED display, keypad, monitor, serial port, and the ability to be able to download programs from PC to run on this computer. And that'll then help us to develop the video controllers, keyboard controller, floppy disk controller, and the BIOS, so we can then start to boot up MS-DOS from a floppy disk. And then later we'll be moving on to add a disk controller, an IDE disk, and then a CGA color video controller, and ultimately see if we can run an early version of Windows 1.0, 2.0. So let's just review the block diagram where we got to. In the previous video, we've done part of this, the reset part of the circuit, and then this video we're going to be adding the 14.3 megahertz clock and the clock circuit itself. So this schematic diagram we looked at in the previous video as well, and this has come from the PCXT schematics in the IBM technical guide. And this one came from the Breadboard 8088 project book. The signal coming from the power supervisor circuit, which includes a reset signal, will be coming in from power good. We're going to be wiring up some form of crystal. You can see here that there are quite a number of the inputs here which are actually tied to ground or 5 volts, so not all of them are required, and some of these inputs we're only going to be using when we've actually got around to writing some of the control logic for the memory wait states and things like that. So the main outputs coming from this circuit will be the ready that goes off to the CPU, the clock 88, which is a special duty cycle, so it's like a two-thirds duty cycle that the 8088 requires. The reset output, which is synchronized with the system clock as well. So the reset signal coming in here and the reset signal coming out there are aligned in the way that is required. We also have the 14.3 megahertz oscillator coming out, and also the peripheral clock, which I think is half the speed of the 8088 clock, only it has a 50% duty cycle. So going back to the 88 project book, there's no substitute for a data sheet, and I know I've mentioned this in the earlier video, but it really is always important to check these. Just to make the point, I was reviewing the Intel 8284 data sheet, and the particular chip I've got is a Fujitsu version of the same chip, but it's an MBL 8284A. I was comparing the diagrams, and one that I noticed is that there was no clock signal identified on the Fujitsu diagram. So you can see here clock, so clock was missing. And also when I was looking through the circuit, I saw that, well, the output of the clock here goes into this one and this one. And when I was looking here, I didn't see anything joining up with those clock circuits. So that dot was in fact missing. So in fact, when you're looking even at manufacturer data sheets, always have a bit of skepticism and cross-reference things with other sources, because sometimes there are mistakes. What I've done on this diagram, all the things which are in green, we're actually directly using the pins. Things which are in black will be tied to ground. Things which are in red will be tied to 5 volts. And I think there's just one input here which we're not actually connecting to anything. So let's now have a look at the rest of the circuit. So we've now configured the power supervisor circuit and watchdog timer. Now we're going to plug in the 8284. We'll just have a look at the data sheet for that. So this is the data sheet for the Fujitsu part that I've got. It is a little bit different from the Intel one, not massively, it's pin to pin compatible, but there are a few differences that we just need to go through. So the main one being obviously the diagram on the front here wasn't quite right, it missed out the clock and hadn't got this connection. So these are all the signals we're doing. So the schematic has already shown all this, but in general, the things we're really interested in, some of these are obviously going to be used later, but we want the FC to be crystal. So we're going to use the built-in crystal rather than an external signal. The clock output is our clock 88 that goes to the processor. That's a peripheral clock. OSC oscillator is the 14.3 megahertz. The res low strobe is actually coming from a power supervisor circuit, so that's the low RST, and then reset is a high signal that goes out to the rest of the computer, and that actually will say when it's high, then it will reset the rest of the computer. We'll probably end up having an inverter on that as well, so we both have a high and a low reset signal. The clock synchronization we're not interested in at the moment, and so that's going to be ground. So that's basically all the things we've got there. There's not much else in this. There's quite a lot of stuff to do, all the timing signals. There was just one thing about the clocks at the end. It's worthwhile sharing. So the circuit that was in the original PCXT was more or less style, but there's some specific text in here that says, with circuit 1, the minimum frequency of crystal was limited to 15 megahertz. Now we're using 14.3, so that's a bit lower. So configuration 1 may cause abnormal oscillation. For a more stable oscillation over the specified frequency range, 12 megahertz to 25 megahertz, configuration 2 is recommended. So that's the reason why we've slightly changed the circuit from the original PCXT one. And again, this is the type of thing that if this was a particular problem, you might spend hours trying to work out why it's not working properly, but in fact it tells you right there. So let's now bring back the board and we'll start plugging in the 8284 and see if we can get the clock working. So I've put on the chip label onto our 8284 clock. We have a 14.3 megahertz clock. I've got a decoupling capacitor. I did add a decoupling capacitor when I remembered I've missed them out. Then we have the 510 ohm resistor to go in parallel across the crystal. 510 ohm resistors will be probably a 1% tolerance. Normally you'd only have a 470 and a 560 ohm resistor with a normal 5% tolerance, so you would need to get a higher tolerance 1% resistor. I just happen to have some here. So we're just going to have a look at the schematic and then I'm going to plug this in. I'll speed it up and commentate over it. Okay, so we're just going to plug in the voltage lines and then we're not going to worry too much about the outputs here at the moment. The main outputs we're interested in is the oscillator output, the reset output and the clock 88. We might also have a look at the P clock as well at some point, but that's not so important. And then we'll just need to make sure that we tie up these various lines to the right, whether you tie them high or low. In particular, the Ready 2 and AEN2 are if you had a multiprocessor design, which we don't need to worry about. So it's just the Ready 1 and the AE1 that's going to be used here. And the EFI is not connected to anything. So I'm just going to unplug some of the test cables I've got here for the moment. So this is the strobe signal, and this is the output from the logic analyzer providing a voltage there. I'm just going to unplug this because this was just my test for showing the different periods for the watchdog timer. So we want to put this in so that it's relatively close, but we also want to make sure VCC is nice and close to these power rails here. So I'll just move these up here a bit to make sure we've got power rails there. Okay, so I'm just going to wire this up and I'll commentate over it and we'll speed it up as well. Okay, so just plug in the power rails, then the decoupling capacitor. Just need to tie that one up to the ground rail there. Do some of the other tying to ground. Actually put those in on the wrong pins when I looked at it from on top. So the other tying to ground, put in the resistor for the crystal, then we just need to move those down and put in the crystal. Then we're just going to plug in the rest of the logic analyzer signals. Okay, so I've wired that up. I've just put in the logic analyzer. So looking at the oscillator output, the 8088 clock and the reset outputs. Now what we do need to do is to plug in the output of the reset into RES here. So at the moment we have the strobe. This is a strobe which I think I'm just going to plug into the P clock for the moment. The strobe is connected to P clock, and then we just need to hook in the output from RST, low RST, into RES. So I'll wire these up properly once we've finished testing this. So what it should mean now is that when it powers up, the reset signal coming out down here will actually follow what's going on over here. If we press the reset button, then the output of reset here will be synchronized with the PC clock as well. So just need to make sure to see we've got a signal out of here, and then we'll be able to see whether or not we're good to proceed to the next step. So I've just added these extra three, so the 14 megahertz oscillator, the clock going into the 88, and the reset output. So I'm just going to kick this off now, or wait. Now what I will need to do is to set this at 200 megahertz to be able to see the frequency of these clocks more accurately. We do need to run it quite fast, but this means I probably won't have time to press the reset button. We'll test that in a minute. So let's just have a look at it first. I'll power this on. Okay, let's just look at the top level. So you can see here, if we add some timing markers, so from when the power is going on around here, we have got about 400 milliseconds, during which time the reset signal coming from the power control circuit, supervisor circuit, is low. Then it comes out of reset here. You can see that there's a signal going into the strobe here, which is something like 2 megahertz, which is what the P clock is supposed to be. That's probably a bit too fast for it. It probably doesn't need to be that fast, but it's good enough for the moment. And we can see down here we've got the oscillator at 14.3 megahertz. You can see at the top right hand side it's slightly under 14.3, 14.285 I think. And then the clock here should be about 4.77 megahertz, and you see it's 476, which is within about 0.2% I think. And if we drill down to look at this, we should see the duty cycle for this particular clock. The 8088 has a 30 sort of 70 type, or a 6633 duty cycle. So if you look at the top right hand side there, it's a 38% duty cycle, so it's close to that. So it looks like we've got the signals that we're expecting. And if we zoom back out to look at this, you can see that the reset signal here goes low to allow the operation of the PC. And the key thing about this circuit as well is it will also make sure that when it comes out of reset, it's at the right cycle in the clock here. So that looks to be working okay. What I'm going to do now is to capture the signal slightly lower, say at 10 megahertz, and that will allow us to record perhaps about 10 seconds worth. And then I'll be able to show the reset button being pressed. So I'm just going to power this off, run it again, and when I power it on, I'm going to press the reset button 3 times. 1, 2, 3. What we should be able to see is the reset button. So we can see here now that the reset button has been pressed 1, 2, 3 times, and that after the reset button has been pressed here, after 20 milliseconds minimum, then we've actually gone into reset. So the fact that we've got low reset signals and high reset signals, and this reset signal is all can be a little confusing, but generally on most other micros, reset is always low. But in this particular case, the main reset signal that goes off to the rest of the PC is actually high in this particular case. So it looks like we've got our various oscillators coming out. You can see here at the top right hand side that because we're recording this at a much lower frequency, that we can't reliably tell what the frequency of the 14 megahertz signal is. But you can see here that when we press reset, that after a few, about 300 or 400 milliseconds, then it comes out of reset. So this is when the reset button is pressed, and then it comes out of reset. In this particular case, it's about 625 milliseconds. That'll be partly because of how long we actually pressed that. Okay, so the circuit seemed to be working. We look back at our KiCad diagram. So the only thing we really need to do now is to wire in this watchdog leads properly, and then we should be ready for the next step, which is to wire in the 8088 microprocessor. And what we'll then be doing is looking to see whether or not we can set this to free run. What that basically means is we set the data bus to be the no operation code, which is 90 hex. what that should do is allow the address lines just to cycle from the power on boot vector all the way back to 0 and all the way up to 1 million and back again. So it just allows us to check to see whether the clock and the CPU is working properly. So thanks for watching. If you don't want to miss out on future videos, please hit subscribe, and if you found it interesting, please hit like. It does help to make the videos available to a wider number of people. Thanks for watching.